All right, welcome to the last video for week 8. Today we're going to be looking at some questions related to the motion of fluids lecture. So let's jump on over to the video, to the slideshow. Here we go, motion of fluids. So we're going to go straight to the questions. We've got 3 questions, as you can see. We've got the chimney is our first question. So there's no real calculation to do here, just a bit of a thought process around what's going on. The question is, it is windy outside, how is the smoke rising up a chimney affected? A, it rises more rapidly in the chimney, B, it's unaffected, C, it rises more slowly, or D, it is forced back down the chimney. So we've got 4 different options. As usual with these videos, I would like you to have a go at the question. Don't rely on just keep watching, follow along and go, oh yeah, I could figure that out. Right? That's a very easy way to trick yourself into thinking you understand, because it's very easy to accept something when it's explained to you. It's a lot harder to do the explanation yourself based on what you know. So do have a go at this. Pause the video if you need to, have a think about it. I'm rambling a bit to try and give you some time to pause, to have a go at it, to come up with your answer, and then we will discuss the solution. So here we go. Here's the solution. When you have wind blowing over the top of a chimney, I just said I didn't really need to write anything, but actually I'm going to jump to our document camera anyway and do a little illustration. Right, so we've got our chimney. Here's our chimney, and we got smoke. So brick chimney, and we got smoke coming up the chimney. It's coming up and going out into the environment. So there's our smoke coming up out of our chimney. And the question is, if we have wind coming past, we've got a windy day and wind is going past the chimney, then what is that going to do to the smoke? Well, you can't really answer this unless you think about what's going on inside the house. So let's add the house on to our drawing. So this is not going to be to scale because I'm not worried about the scale of our house. But let's add this house on. Here we go. And so this is a nice big fireplace with a big roaring fire going, making all that smoke. The question is, what is the air pressure inside here going to be? Well, hopefully you'd all agree that it's likely to be around about atmospheric pressure. There's no reason that it would be any different. Yes, we've got a fire going, which might heat it up, and if you know anything about temperature, you know that heating a gas will increase the pressure, but it's not going to make it really hot. It's only going to make it a nice, comfortable temperature, and furthermore, we've got the smoke going out the chimney, so clearly it's open, so if it got too high, the pressure of heating the environment would increase it up, push it up the chimney further. So we'll just say it's around about atmospheric pressure. So we've got around about atmospheric pressure. Inside, at the bottom of the chimney, what's the pressure above the chimney on the outside? And that's really where this question becomes, the discussion from our slides becomes relevant. And we've been told that it's a windy day, so we've got some wind. It doesn't matter which direction it's going, just that it is going past the chimney. And if that wind is going past, so our still air in here has a velocity, has a atmospheric pressure, then if this is greater than 0, velocity greater than 0, we must have pressure less than atmospheric, right? Because faster the fluid moves, the less the pressure is. So if this fluid is stationary and it's atmospheric, this is faster, it must be less than atmospheric pressure. So now we've got pressure less than atmospheric here, and we've got atmospheric pressure here. So we have a pressure difference. Right, there is a difference in pressure between the bottom and the top of the chimney, and that means that we are going to get a net force upwards, right? So there will be a force upwards on these, on the smoke rising in the chimney. So the answer is, after all of that discussion, the answer, we'll jump back to our slides. The answer is A, it will rise more rapidly in the chimney. So you may have just come to that conclusion very quickly and not needed as long as I took to explain it, but hopefully following along with that explanation leaves you with no doubt that the smoke will in fact rise more quickly up the chimney. As usual, some answers written into the slides for those of you that prefer just following along with the written slides and not watching these videos. Next question, pipe diameters. The diagram shows gas flowing through a hidden pipe which has changing diameter. Liquid is connected to the gas pipe at 3 locations and sits at different heights at each location. What can we determine about the diameter of the hidden pipe at each location? So you can see at point A, the liquid is only here, halfway up. At point B, it's almost all the way up. And at point C, it's a lot lower. It's only just started. So as it says, what do we know about the hidden pipe? There's a hidden pipe. So this grey box is not the pipe. It's just something hiding the pipe. It's like a curtain in the way. The pipe is behind it, and we don't know what it looks like. So we'll go back to our document camera. Move away from our fireplace drawing, and we'll think about this one. So I'm just going to sketch this out again to start with. Just write out what we already know. We've got point A, point B, and point C. And we don't know what the pipe looks like, but we know what the bit underneath it looks like. Right. And the bit underneath it we saw has liquid all the way up B, only a tiny bit up C, and about halfway up A. Right. So if this is all connected, then we know that the pressure here along the bottom is the same everywhere. Right. So this pressure is constant all along the bottom, and that means that the pressure here, right, so the pressure at this surface is going to be the greatest out of these 3 pressures. So pressure at C here is the greatest, pressure at B is the least, and pressure at A is in the middle. So we've got pressure C is greater than pressure B, which is greater than, no, pressure A, which is greater than pressure B. Right. So we know that because if this is the highest, then as you go down, it has to get greater in pressure. And this is all connected, so the pressure at A has to be the same as the pressure is here. Right? And the pressure at C has to be the same as the pressure is here. So you can see that B is going to be the least pressure, then A, and then C is the most pressure. So that's just thinking about the liquid based on what we know about pressure and depth in a static fluid. Because this is static. Yes, the gas through our pipe is in motion, but this is a static fluid. But the heights here are what we're looking for. So now we need to think about the pipe. So we don't know anything yet, so I'm just going to draw a dotted straight through pipe. If this was the case, if the pipe was just constant, without changing all the way along, then that would mean that the velocity here is the same as it is everywhere. Right? And we would have the same velocity everywhere, we would have the same pressure everywhere. Right? But if we had the same pressure here, then this would be at the same height as this, because they'd be subjected to the same pressure. So just to explain that a bit further, remember that if you've just got a tub of water sitting there, then you've got P atmospheric pressure, pushing down all over the surface of it. Right, that's how gases and fluids interact. The gas applies a pressure to the surface of the fluid. And so here, if this gas was at the same pressure everywhere, it would apply the same pressure to the fluid everywhere, and all 3 columns would be the same height. That's what we would see if it was a constant diameter pipe all the way along. But it's not, right? It can't be, because we have these 3 different pressures. So now we have to think about what happens, what would cause these different pressures. And again, this is just like we saw on the chimney one. The different velocity is going to result in a different pressure. And we know that a faster velocity is going to be a lower pressure. So the lowest pressure here, PB, must have the highest velocity. So that means our velocity at B must be greater than the velocity at A, which must be greater than the velocity at C. So the velocities are the other way around. We've got the slowest velocity at C, which results in the highest pressure. and therefore pushes the most down on the fluid. We have the greatest velocity at B, which results in the lowest pressure and therefore can't push the liquid down as far as the other two. So that's what we must have in terms of the velocity. And then the last part of the question is to actually describe the pipe. What does it look like? Well, if velocity at B is the fastest, it must be the narrowest at B. So we must have narrowest at B. A is in the middle, so it must be in between. And C is the highest pressure, therefore lowest velocity, therefore it must be the widest. Right? So we don't know exactly what the pipe will look like, but we know that it'll be some diameter here. It will get narrower, right? It'll get narrower as it goes past B, and then it'll get wider than it even was originally by the time it gets to C. So that's the answer to that question by considering the different pressures. So we're actually bringing in our our static fluid pressure discussion with that liquid, and then bringing in our dynamic fluid discussion with the shape of the pipe and what that does to the velocity and therefore the pressure. So a nice question that brings in multiple parts. As usual, we've got the answer written out in the slides as well. Right, and our third question, a clogged artery. If an artery has a blood flow of 0.2 meters per second, and then a blockage reduces the area to a quarter, so area to a quarter, not by a quarter. I think this slide has had some issues in the past, so it may be incorrect on the answers, but we'll follow along and see what we get. So if the area is reduced to a quarter, we want to calculate A, the speed through the clogged portion, and B, the difference in pressure. Sorry, just jumped forward before you're ready. Difference in pressure in the clogged portion of the artery compared to the normal pressure in the unclogged artery. The density of blood is 1.06 times 10 to the 3 kilograms per cubic meter. All right, so let's have a think about this one. So this is just the same concept as we've been doing, but now we just happen to be talking about blood in an artery. So we've got an artery. Or was it an artery or a vein? I can't even remember. Yeah, it was an artery. So we've got an artery, and we've got whatever the area is here. All right, so this is some area A, and we have blood flowing through it at, what was the velocity, 0.2. So V initial is equal to 0.2 meters per second. So that's our initial scenario. And then we're saying we've had some clogging, some buildup of plaque or something that has narrowed our artery. All right, it's narrowed the artery, and it's now got to squeeze through this this little bit here, and the area here is equal to a quarter of our initial area. All right, so that was the initial. This is our final. So the initial area is now reduced, and it's got to all narrow down into here to get through that clogged bit. Right. So what is that going to do to the velocity here? Well, hopefully you can all remember the continuity equation, because that's all we need for this bit. We know that if it's going to get narrower, it has to get faster. So we expect a faster result. We want V final, or V clogged, or whatever you want to call it, is greater than 0.2. This isn't my calculation, this is just a note to myself. Thinking about the scenario, this is what I expect. Right? So it's always good to just have that in mind. We expect something greater. So now let's look at our equation. We know that A1 V1 is equal to A2 V2. We're looking for V2, so V2 is equal to, divide both sides by A2, A1 over A2 V1. And we know that A2 is a quarter of A1, so that means V2 is going to be 4 times V1. So this is very similar to the example we had during the lecture, that the velocity here is now going to be 4 times what it was before. So that means we've got 0.8 meters per second, and as we expected, yes, it's more than 0.2, which is good. So that's our velocity. That was the first part of the question. The second part is, what's the pressure here compared to here? Now, we don't know the original pressure. We don't know P1. We'll call it P1. We're looking for P2. We don't know P1, but we can find the difference in pressure. All right. So if we think, here's our first point, we have pressure 1 plus half rho times V1 squared. Everything's at the same height. We're going to assume same height since we haven't been told anything about that. So we're going to have none of our rho g y terms. It has to be equal to pressure 2 plus a half rho V2 squared. So we're looking for pressure 2 compared to pressure 1. So if we just move this term over the other side, and then I'll write it around the other way, P2 is equal to P1 plus a half rho, oh, I forgot the plus a half rho V1 squared, and then minus, because we moved it over, minus a half rho V2 squared. So we've got pressure is equal to this thing, and we know everything here now apart from P1. So we're going to get P1 plus some number. And just thinking about it, we have a faster velocity, and we expect the pressure to drop. Right? We expect the pressure to drop. So we actually expect this to be a negative number, not a positive. So that's my little expectation, is that we're going to get a lower pressure. So it'll be P1 minus something. And for that to be true, this term, the negative, must be bigger than this term. And since V2 is bigger than V1, that makes sense. And so now you can grab your calculator and put in all your values. We got told the density of blood was 1,060. So rho equals 1,060 kilograms per cubic meter. So if you put that in, you'll find that it comes out to negative 318 Pascal, according to my calculation, I think. I think that's right, hopefully. So you can double check that. Let me know if I've done it incorrectly, but I got 318 Pascal less. So we still don't know what P1 is, and we don't know what P2 is, but we know that P2 is 320 Pascal less than P1. And why is that important? Why do we care that the pressure is dropped in the middle of a clogged artery? Well, sorry, just clicking too many buttons on my screen. Well, if the pressure drops where that clog is, then the pressure around it is still the same, the pressure from the rest of the body, because remember, this artery is in our body is exposed to atmospheric pressure, so there's constantly 101,000 Pascal pressing on us from the atmosphere, and therefore all of those particles that make us up are all subjected to that pressure, and they'll apply that pressure onto the particles in the next layer. So our skin will be applying that to our muscles, and that will be applying it to the all the arteries and so on, and then everything applying it to the bones and so on. So everything in our body is all under pressure constantly. And so if you go and make a part of one of our blood arteries or one of our arteries or veins or something lower pressure, then that means everything else is still pushing on it, and it might collapse. And so when it gets too clogged, it can actually collapse, and then you have no flow at all. And obviously, that's not a good outcome, right? So that is why it's important to understand these fluid flow rates and things for biological systems, because it can tell us when they might actually fail. We could then look at the structural integrity of arteries and veins and figure out what pressure differential would cause it to collapse, and therefore know whether people are likely to be at risk of their arteries and veins becoming fully blocked rather than just slightly blocked with a clog. Anyway, that's getting a bit to an aside. It is relevant and it is important, and hopefully you can see that it does have use regardless of what discipline you're in. But that, I believe, is the end. I'll just double check. That was the last slide. So those are the three questions. Hopefully they'll help reinforce some of those concepts, especially that last one, using Bernoulli's equation. That's the thing that, as I said, most people need quite a bit of practice with, just getting used to applying that equation to different scenarios. So choosing 2 points and making them equate. So that's the end of the content for week 3. For those of you that are going to come along to the video tutorial, there will be Wednesday 5 p.m. That's today, in about an hour after I post this. There will be a video going through a past exam problem. Otherwise, I will see you at the workshop on Friday.